Last time, we developed iterated integrals with respect to Lebesgue integrals of sigma finite measures and used that to construct product measure. That is, given two sigma finite measure spaces, we can construct a measure space over the Cartesian product, the sigma field being the product sigma field that we developed in the previous lecture, and the measure being defined by an iterated integral. That is, we take the indicator function of any event in the product sigma field and we integrate it against one of the measures in one of the variables, leaving a new function that we can integrate against the other measure and the other variable. We showed that this makes perfect sense and that it doesn't matter which order we do the integration, we'll get the same answer. We could get infinity as an answer, of course, but since the function that we're integrating is a non-negative function, there's no ambiguity about what kind of answer we'll get. It will either be a non-negative real number or infinity. If the measures mu1 and mu2 are finite measures, then of course we will get a finite number. And this defines a measure. It's the unique measure that satisfies the rectangular property that the product measure of a product set is the product of the measures of the sets. Great. So now we have a measure, and now we can do Lebesgue integrals of functions with respect to that measure. But we should be able to reduce that to integration of the original measures mu1 and mu2 that we started with, and indeed we can. We'll begin with Tonelli's theorem. Tonelli's theorem says that, hey, since we constructed this thing as an iterated integral, integrating against that measure is going to be an iterated integral, at least in the case where the function is non-negative. If f is any non-negative product measure Borel measurable function, then integrating it against the product measure can be computed by doing an iterated integral. And once again, it doesn't matter what order we do the integration, we'll get the same answer either way. This actually follows almost immediately from the definition up here by the standard method of defining integrals of non-negative functions approximating by simple functions. If we call this equation star, then we simply note from the definition that star holds for functions of the form indicator of any measurable set, measurable in the product sigma field. And therefore, by linearity of everything on both sides, it also holds for f1 product f2 simple functions. That is to say, the left-hand side is a linear functional of the input function f, and so is the right-hand side, because integrating this with respect to one of the inside measures is linear as a function giving values in functions of the other variable, and then the outside integral makes that into a linear functional. And so we can track that through over linear combinations of indicator functions, and the equality will still hold for simple functions. But hey, if f is measurable and non-negative, then I can approximate f by a non-decreasing sequence of measurable simple functions. In fact, I have an explicit formula for how to do that by dyadic decomposition of the range of f, if I want. The fact that the phi n's increase to f mean that if I integrate the phi n's, I will get an increasing sequence that converges to the integral of f by the monotone convergence theorem. And the same thing will hold for the inside integral here, holding almost any of the other variable fixed, and then again by the monotone convergence theorem over here. And so we'll just say that the equation star holds by 3 applications of the monotone convergence theorem. And that is the proof of Tonelli's theorem. So now we know how to integrate non-negative functions, at least, as iterated integrals. Let's do the most fun standard example that's usually done in a probability course, and let's confirm what the right integration constant is for the standard normal distribution. Here we have a density, which is a constant times e to the minus x squared over 2. We know that that density is supposed to be 1 over the square root of 2 pi in order to make that a probability density, to integrate to 1. Well, we can use Tonelli's theorem in a clever way to compute that, even though actually integrating e to the minus x squared over 2 is not that easy from the perspective of a calculus class, since that function doesn't have an explicit antiderivative in simple terms. Well, first let's note that the function e to the minus x squared over 2 is a non-negative measurable function. In fact, it's continuous. So let's let I be its integral, which a priori might be infinite, but is a well-defined non-negative real or infinite number. And then we do this fun trick. We take the square of that Lebesgue integral and write it like this: the integral of f at x dx times the integral of f at y dy. And then we recognize that as an iterated integral. We can take this constant and move it inside and realize that that's exactly what happens when you do an iterated integral of a tensor product function, as we saw in the previous 2 lectures. And so by Tonelli's theorem, this is the same thing as the integral over the product of that tensor product function against the product Lebesgue measure. The product Lebesgue measure on the product sigma field being the Borel sigma field over R2 is nothing other than the 2-dimensional Lebesgue measure by definition. Now, what is this function f tensor f? Well, it's the function that takes xy to the product f at x times f at y. But using products of exponentials, that's the same thing as e to the minus x squared over 2 minus y squared over 2, or e to the minus 1/2 of x squared plus y squared. Now the trick here is to note that that thing in the exponent has nice rotational symmetry. And so what we're going to do is compute this Lebesgue integral using the monotone convergence theorem by first integrating over an increasing family of compact subsets. And those compact subsets will be disks centered at the origin. If we let dr be the disk of radius r centered at the origin for any non-negative r, then those disks fill out all of R2 as r goes to infinity. And therefore, if I integrate my function f tensor f over that disk and take the limit as r goes to infinity, that will give me the integral over all of R2 by the monotone convergence theorem. Critical here is the fact that f is a non-negative function, so that f tensor f times the indicator of this disk is an increasing family of functions as r increases. Now this integral can be computed using plain old Riemann integration theory, because the function f tensor f, written right here, is a continuous function, and the domain is a compact set. Using Riemann integration notation, this is the double integral over the disk of radius r of that function e to the minus 1/2 x squared plus y squared dx dy. And now we'll use the change of variables theorem to convert this to polar coordinates and write that as the integral of d theta from 0 up to 2 pi of the integral from 0 up to r of r dr times the integrand, which in polar coordinates is e to the minus r squared over 2. And the beauty of doing this is that the integrand function inside here, r times e to the minus r squared over 2, has an explicit antiderivative. It's minus e to the minus r squared over 2. And so when all is said and done, this explicit integral is 2 pi times 1 minus e to the minus r squared over 2. So we're supposed to just take the limit as capital R goes to infinity in order to recover the integral I squared. And of course, as r goes to infinity, this just goes to 2 pi. Which means, therefore, that I squared is equal to 2 pi, and so I is equal to the square root of 2 pi. And therefore, to get a probability density, we need to divide this by the square root of 2 pi. If you'd like to see some more fun examples of how one can compute some explicit integrals by interpreting them in terms of double integrals and then using Tonelli's theorem in a creative way, I recommend you see some examples in section 13.3 of Driver's Notes. That being said, in many of those cases, Tonelli's theorem doesn't apply because the functions one is hoping to integrate are not non-negative. In general, we're going to need to be able to integrate non-negative functions against product measures and still do it in an effective way. And that's where Fubini comes in. Fubini's theorem is the counterpart to Tonelli's theorem in the case where the integrand function is not non-negative. So now we have to be a little careful because, as we know, integrating a function that can take both positive and negative values can be problematic. We can get infinity minus infinity problems, and so we usually leave out the possibility of that and restrict to the case where the positive and negative parts are both integrable. So we need to be clear on what integrable means in terms of the original measures when we're integrating against the product measure. And Fubini's theorem is a fairly long statement which says how all of that works. Here's the idea. We start with any measurable function on the product space with respect to the product measure. We'd like to know when such a function is actually integrable. When is it in L1? And Fubini's theorem says that it's in L1 if and only if the iterated integral in either order of the absolute value of the function is finite. Well, that's not news because Tonelli's theorem tells us that either of these two iterated integrals is equal to the integral over the product of this non-negative function. And so the equivalence of those three is an immediate consequence of Tonelli's theorem. But that's just the beginning of Fubini's theorem. In this case, that f is L1 with respect to the product measure, we have the following. The integrand function without absolute values is an L1 function of either of the two variables, treating the other variable as a constant. That is, as a function of omega 1, f of omega 1 and omega 2 is L1 for almost every omega 2, almost every with respect to the measure, mu2, and vice versa, treating omega 2 as the variable. Moreover, now that we know that it's L1, we can integrate it. And once we integrate out the variable omega 1, we get a new function of omega 2, and that function is L1, and vice versa, reversing the roles of the two variables. And finally, the integral of f against the product measure, which is well defined since f is in L1 under this assumption, can be computed as the iterated integral, and of course it can be done in either order, giving the same finite real number answer. So that's what Fubini's theorem says, except not quite. I've lied to you a little bit because there is a subtle problem. Here we see, for example, that the function of omega 1, treating omega 2 as a constant, is L1 for almost every omega 2. But what about those omega 2s for which it's not L1? Well, for those omega 2s, this function doesn't make sense. And it's not just that it might give infinity as an answer, it just might not give an answer. We could have an infinity minus infinity type situation, and there's no consistent way to give that integral a value. So in order to take care of that, what we'll do is once we know there is a null set on which this problem can come up, we're going to modify f on a null set in each variable in order to get rid of this problem. Now the notation I'm going to use for that is to say, actually we're going to call this slash integral. And that slash integral means that, hey, for those omega 2s for which this didn't make sense, we'll just define that half integral function as 0. That is unavoidable. And we'll see that because we're only modifying things on a set of measure 0, it's not really going to affect what happens. But it is important to be clear because as we stated this without the slash, this just doesn't make sense. So let's get into the details. Let's look at that set, E1, for example, with respect to the variable omega 1. The set where treating f as a function of omega 2 for fixed omega 1, it is not integrable in absolute value. In that case, trying to integrate this without the absolute value bars could produce nonsense. Well, we want to see that that exceptional set of bad omega 1s is negligible. Let's denote this extended real valued function of omega 1 as I of omega 1. By Tonelli's theorem, this function I is f1 Borel measurable. That's Borel measurable with respect to the extended real line. And therefore, this set E1, which is the preimage of I on the singleton infinity, is f1 measurable. Now, since f is assumed to be an L1 function with respect to the product measure, the integral over omega 1 of I of omega 1 is equal to the integral over the product space of the absolute value of f, and is therefore finite. But that function I, which is an integral for each omega 1 of a non-negative function, is a non-negative function of omega 1. So we have a non-negative function that integrates to a finite number. As we've proved before, it therefore follows that that function is finite almost surely. But that's exactly to say that the set E1, where it takes the value infinity, has measure 0, which is what we hope to establish. A very analogous argument shows that the set E2 of omega 2, where the integral with respect to omega 1 is infinity, is a measure 0 set as well. And so that verifies the first two conditions of Fubini's theorem. Now, as noted, even though this exceptional set, where that inside integral can blow up in absolute value, is negligible, nevertheless, if we want to define a new function to be the same as this integral but without the absolute value bars, that's only going to make sense off of the set E1, and similarly off of the set E2 when we're thinking of it as a function of the other variable. And so accounting for this ill-definedness on a negligible but non-empty, potentially, set, we introduce this new notation, as I intimated on the previous slide. Given any measure nu and any real-valued or even extended real-valued function g, we define the slash integral of g against nu to be our definition of the Lebesgue integral, if it makes sense, if that g happens to be an L1, and we just give it the value 0 otherwise. So that means that the integral here, without the absolute value bars, is defined for every omega 1. If omega 1 is not in the exceptional set E1, then it's given the value that the Lebesgue integral gives it, because as we just showed, this function, which is the L1 norm in the other variable, is finite. On the exceptional set E1, we give it the value 0, and so now it's defined everywhere. We've modified it from being defined almost everywhere but ill-defined on a set of measure 0 to being defined everywhere. Doing so is just a technicality, but is important. It won't change the value of the integral. We could have defined it to take the value 17 instead of 0, and it wouldn't change the value of the integral when we do the outside integral. But it's convenient to define it to be 0 so that we have the following representation. If we now integrate with the slash the function f of omega 2 for fixed omega 1, that's just the same as integrating the function times the indicator of the complement of that exceptional set in omega 1, because this just sets the value equal to 0 when omega 1 happens to be in the exceptional set E1. That's convenient because now that we know that f of omega 2 for omega 1 everywhere is integrable, by definition of the Lebesgue integral, I can write this as the integral of f plus minus f minus. Now, if I distribute this indicator through the difference here, and notice that the positive part of this product is just this times the positive part of f, given that this is a non-negative function, then by definition, this becomes the integral over omega 2 of this indicator times f plus minus the integral over omega 2 of the indicator times f minus. Now let's be careful here. In order to do that, we needed that the function involved here is measurable with respect to f2. on the space omega 2. Well, to see that that's true, we just note that the indicator function of the complement of that set can be thought of as a tensor product. It's the indicator function times the constant function 1 of the two variables. And so therefore, these integrands here are actually a product of a manifestly measurable function of the product space. So the inside function here is measurable on the product space. It's also non-negative, and therefore, by Tonelli's theorem, this integral as a function of omega 1 is f1 measurable. The exact same argument applies to the second integral here, and so therefore, by Tonelli's theorem, we have that omega 1 mapping to this slash integral of f of omega 1, omega 2 is f1 Borel measurable. That's almost the second statement of Fubini's theorem. We wanted to show that it's integrable. Measurability is certainly required for that. We also need to see that the integral of the absolute value, now knowing that it's measurable, is finite. Well, let's just use the basic properties of integrals here. The integral with respect to omega 1 of the absolute value of that function is, using the triangle inequality inside, less than or equal to the integral of the inside integral, which I'll write from its definition as the indicator of E1 complement of omega 1 times the absolute value of f of omega 1, omega 2 against mu 2. Now this is an iterated integral, and this function is constant with respect to the inside integration variable, so we can pull it outside, which means that the outside integral is just integrating over E1 complement, which is a full measure set in omega 1. So again, by Tonelli's theorem, this becomes the integral over E1 complement times omega 2 of f against the product measure. Well, E1 complement times omega 2 is a subset of omega 1 times omega 2, and f is an L1 function on the whole space, and therefore this is finite. Of course, whatever value we get here is equal to the L1 norm, since this is a full measure set in the product set. So we've now verified the second condition of Fubini's theorem. The inside integral, modified on a set of measure 0, so it makes sense, is an L1 function, which means we can integrate it with respect to the other variable. All we've left to do is verify that that iterated integral doesn't care which order we do it in, and actually produces the Lebesgue integral with respect to the product measure. So let's verify that. Here I've chosen to do the iterated integral in the order that we've been doing it so far. I'll integrate on the inside with respect to omega 2, and then on the outside with respect to omega 1. By definition of the slash integral and Lebesgue integrals of functions that aren't necessarily non-negative, this inside is just broken up as the difference of those two integrals. And now using the linearity of the outside integral, we get that this whole thing is defined to be a difference of these two integrals, since these are both non-negative functions of omega 2, and therefore are the positive and negative parts of those functions, which are, we've just verified, L1. And now, having expressed this as a difference of two non-negative functions, in each case we can apply Tonelli's theorem to write the terms as an integral over E1 complement times omega 2 of f plus minus an integral over E1 complement times omega 2 of f minus. As we noted on the previous slide, this is a full measure set inside omega 1 times omega 2, so we'll go ahead and just replace it. We know that won't change the value of the integral, and therefore this is the definition of the Lebesgue integral over the product space of f d mu1 tensor mu2, since, as we verified, each of these inside is an L1 function. And that concludes the proof of Fubini's theorem. It is sometimes referred to as the Fubini-Tonelli theorem, although probably should be the Tonelli-Fubini theorem, despite the reverse alphabetical order, It's clear that Tonelli's theorem is a key ingredient at all of the steps for proving it. Fubini's theorem will be a key tool that we'll be using in many applications for the rest of the course. It's also the final, purely measure-theoretic, integration-theoretic topic that we needed to cover. From here on out, we'll be heading straight into probability territory.